Hello and welcome to the Section 4.6 lecture video. Section 4.6 is all about curve sketching, and the general idea is given a function, we can learn a lot about the shape of the function via its first and second derivative. Okay, the first derivative can either be positive, that means the function is increasing, or it can be negative on an interval, and that means the function is decreasing. Also on an interval, the second derivative can be positive, which means we're concave up, or the second derivative can be concave down. Down with an N. And so that gives us four real shapes that a function can have on an interval. If we are plus plus, so that means the first and second derivative are both positive, we're increasing in concave up, the shape of the function is something like this in the top left. If we're plus minus, so that means the first derivative is positive, the second derivative is negative, we're increasing in concave down, so the shape of the function is something along these lines here in the top right. If we are minus plus, so that means we're decreasing and concave up, then the shape of the function has to look like this. And then lastly, if we're minus minus, so we're decreasing and concave down, then the shape of the function looks something like this. This is pretty much the worst way your stocks can go, is minus minus. In order to help us graph these functions, to sketch these curves, there are two really important things. One is transition points. So transition points are the points where the basic shape of the graph can change due to a sign change of f prime or f double prime. When I say a sign change, that means either the first derivative or the second derivative switches from positive to negative or negative to positive. These are also known as our local mins and maxes or our points of inflection. Okay, when I say the basic shape of the graph, I mean at a transition point, the shape of the graph might go from something like this to something like this. Okay, we're going to change from one of these basic shapes to another one of these basic shapes. And then lastly, the other thing that's helpful is the asymptotic behavior. So that means how does the function behave as x approaches positive or negative infinity? How do we actually go about this? Well, here's a little blueprint. Step one is we determine the asymptotic behavior. So that means we take the limit as f of x goes to infinity or as x goes to negative infinity. And that tells us how the end points of the graph, or the end behavior of the graph, what's happening at the end. Okay, and then we're going to use the first derivative test to find the intervals of monotonicity and the local maximums and minimums. And then we're going to use the second derivative to find the points of inflection. We know how to do this. We've done this for the past couple sections. And I just want to note that these points of inflection and the local maximums and minimums are called transition points. And as always, we want the x, y values. Because we're going to plot this, we want to know where the x's and the y's go. Okay, lastly, once we find our transition points, we're going to use those to break the number line into intervals and get a sense of the general shape of the function on each interval. And once we have that, we can draw the graph. We draw the general shapes of the graph on those intervals and just kind of glue them together. But how does this look in practice? Okay, let's say we're given a function like f of x equals x squared minus 4x plus 3. We want to sketch it. So step one is let's take a look at the asymptotic behavior. So the limit as x goes to infinity of f of x is, well, since we have a polynomial here, and we know that as x goes to infinity, the behavior of the entire polynomial becomes essentially the same as just this first leading term. We know that the limit as x goes to infinity of our given function is the same as the limit as x goes to infinity of x squared. And I should note here, when I say leading term, I mean the term with the highest exponent. Okay, so for this here, the limit is clearly infinity. Okay, so that means as x gets really big, the function also gets really big and positive. And then similarly, the limit as x goes to negative infinity of our function is the same as the limit as x goes to negative infinity of x squared, which is again positive infinity. So we know that the endpoints of the graph are trending upwards. Okay, we'll take that into account later. Now let's find our transition points. Okay, to find our transition points, we're looking for local maximums and minimums and points of inflection. And we do that by taking the first derivative. So here f prime of x equals 2x minus 4. we can set that equal to 0, and we have that x equals 2 is a critical point. And we're going to use this information to find our intervals of monotonicity, right? Because that's what we're supposed to do in our blueprint. It's supposed to find the intervals of monotonicity. We use this critical point to break the number line into two intervals, from negative infinity to 2, and from 2 to infinity. We pick a number from both of these. I'll pick 0 and 5. And we plug into the first derivative. So f prime of 0 is minus 4, is less than 0. And f prime of 5 is 10 minus 4 is 6, is bigger than 0. So that means f prime is bigger than 0 on the interval from 2 to infinity, and f prime is less than 0 on the interval from minus infinity to 2. And what does that mean about our point x equals 2? It means that that must be a minimum, right? Because we're decreasing to the left of x equals 2, we're increasing to the right of x equals 2. So minimum at x equals 2, we plug x equals 2 into the original function because we want the xy coordinate pair for our local minimum. We find that f of 2 is 2 squared minus 4 times 2 plus 3. So this is 4 minus 8 plus 3. This is minus 1. So we have a local min at the point 2 minus 1. So that's one of our transition points. The other transition points we might have are at points of inflection. And in order to find points of inflection, we take the second derivative. So here's our first derivative. We're going to take the derivative of this. We find that f double prime of x equals 2, which is greater than 0. So we are concave up everywhere. And so there are no points of inflection. So this is kind of an easy case to work with because there's only the one type of transition point. Okay, and with this in mind, we can take our number line. We plop down all of our transition points. We only have the one. And we look at all the intervals that we get from that. So we have an interval from minus infinity to 2 and an interval from 2 to infinity. And we're going to take a look at the first and second derivative on these intervals. As we already found on the interval from minus infinity to 2, the first derivative is less than 0. So negative. And on this other interval here, we already found that the first derivative is bigger than 0, so positive. And then lastly, when it comes to the second derivative, we found that it's positive everywhere, so it's positive on both of these intervals. And so that means that on this interval here, the general shape of the graph is decreasing and concave up. And what does that mean? That means we're looking at something like this. So the general shape of the graph is this on this interval here. And then on this interval from 2 to infinity, the general shape of the graph is this because both are positive. We have a plus plus, which means we're increasing concave up. And we can use this information to actually plot our graph. Okay, so we found we have a local minimum at 2, negative 1. And then we know that to the right of 2, we're increasing concave up. And to the left of 2, we're decreasing concave up. And so the shape of our graph looks a little something like this. We can call it a day. And if we want to, we can put these arrows here. And these arrows at the ends indicate that the function continues in this manner. So this says, hey, as we continue going to the right, our function continues up. This says, if we continue going to the left, our function continues going upwards. Let's take a look at a slightly more complicated example. Let's say we have this function here. So this is a cubic function. It's cubic because it's a polynomial, and the largest exponent is a cube, is 3. So what do? we take a look at our asymptotic behavior first and foremost, even though it tends to not come into play as often as the other things, but it's still important. Again, since this is a polynomial, the limit of the entire function as x goes to infinity is the same as the limit as x goes to infinity of the leading term, 1/3 x cubed, which in this case is positive infinity. And then the limit as x goes to negative infinity of the function is the same as the limit as x goes to negative infinity of 1/3 x cubed, which in this case is negative infinity. We get this negative because if we plug a negative in here and we cube it, so we take a negative number times itself, we get a negative number as an output. So we found the asymptotes, or we found the asymptotic behavior. And now let's find our transition points. Okay, we begin by finding our critical points. We take the derivative, we get x squared minus x minus 2. We set that equal to 0. We can factor this out to be x plus 1 times x minus 2, equals 0. And so this means we have x equals minus 1 and x equals 2 are the critical points. And from here, we can use those to break the number line into our intervals. Into our intervals of monotonicity. So we have an interval from minus infinity to minus 1. We have an interval from minus 1 to 2. And lastly, we have an interval from 2 to infinity. We're going to pick a number out of each of these. I'll pick minus 2, 0, and 10. Okay, we're going to plug those into our first derivative. F prime of minus 2 is minus 2 squared minus negative 2 minus 2. So that's 4 minus 2, which is negative, is less than 0. F prime of 0 is 0 squared minus 0 minus 2. And that gives us minus 2, which is less than 0. And then lastly, f prime of 10. What do we get? We get 10 squared minus 10 minus 2. So that's, 100 minus 10 is 90 minus 2 is 88, which is definitely bigger than 0. And hold on a minute, sorry. This should be a positive. This should be a plus, because we're subtracting off a negative. So it should be a plus 4. We get 6, which is bigger than 0. My apologies. You'd almost think I should edit that out, but I won't. So what does that mean for us? This tells us that f prime is bigger than 0 on the following intervals. The interval from minus infinity to minus 1, and the interval from 2 to infinity. And then the f prime, the first derivative, is less than 0 on the interval from minus 1 to 2. So what does this tell us about our critical points? At x equals negative 1, what do we have? That's right, we have a local maximum. And we also similarly have a local minimum at x equals 2, because the derivative changes from negative to positive at x equals negative 2. And so let's plug these into our original function. Okay, in order to help us do that, I have a calculator here. Isn't that handy? So we have that f of x equals 1/3 x cubed minus 1/2 x squared minus 2x plus 3. And we want to find f of minus 1 and f of 2. Okay, so that's 25 over 6, 4.16, and minus 1/3. So let me write that down. We have a local max at minus 1, comma 4.167, and a local min at the point 2 minus a third. Okay, so these will become helpful. We're going to plot these points. And then the other type of transition points we have are our points of inflection. And let's find that. We find that by taking the second derivative. So we have the first derivative up here. When we take the second derivative, we will get 2x minus 1. We can set that equal to 0, and we find that x equals 1/2 is a possible point of inflection. And with that information, we break the number line into two intervals, one from minus infinity to 1/2, and one from 1/2 to infinity. And we're going to pick points from both of these. I'll pick 0 and 1. And we're going to plug into the second derivative. Okay. F double prime of 0, we get 0 minus 1 is negative 1, which is less than 0. And f double prime of 1 is 2 times 1 minus 1, that's positive 1, is bigger than 0. So that means we are concave up on the interval from minus infinity to 1/2, and we're concave down on the interval from 1/2 to infinity. Because the second derivative changes sign here, that tells us that this is indeed a point of inflection. And so let's get the x, y values for this point of inflection. So we're going to plug this x equals 1/2 into the original function. Let me flip back to my calculator. And we have f of 1/2 is 1.916. Okay, flip back over here. So we have a POI at the point 1/2, 1.916. Okay, so we have our critical points and our points of inflection. What do we do with those? Well, we take our number line and we plop down all the points that we found. So we found important points at x equals 1, x equals 1/2, and at x equals 2. These are critical points, local maximums, minimums, and then this is a point of inflection. And we figure out the shape on each of these intervals here. So this means we have an interval from minus infinity to minus 1. We have an interval from minus 1 to 1/2. We have an interval from 1/2 to 2. And we have an interval from 2 to infinity. We're going to take a look at f prime and f double prime on everything. Okay, since we're right here, let's take a look at f double prime. We're concave up on everything less than 1/2 and concave down on the interval from 1/2 to infinity. So that means for things that are less than 1/2, intervals here and here, that means the second derivative is positive on both places. Shoot, I mean negative. Goodness. You'd almost think I would edit that out as well. But again, I won't. These are both negative. My apologies. And then on intervals that are bigger than 1/2, so the interval from 1/2 to infinity, the second derivative is positive. So we're looking at something like this. And what about the first derivative? What do we know? Well, we know the first derivative is bigger than 0 on the interval from minus infinity to 1 and from 2 to infinity. So we're positive on the interval from minus infinity to minus 1 here, and the interval from 2 to infinity. So we're positive there. And then we also know that the first derivative is less than 0 on the interval from minus 1 to 2. The first derivative is less than 0 on the interval from minus 1 to 2. So that's this interval here, the first derivative is negative. What do we do with this information? Well, once we know the shape, once we know the signs of the first and second derivative on these intervals, we can see what shape they correspond to. Plus minus, that means we're increasing and concave down. That means we look something like this. Minus minus on this interval means we're decreasing and concave down. So that means we look something like this. Minus plus means we're decreasing and concave up. So that means we look something like this. And then lastly, both first and second derivative being positive means we're increasing and concave up. So it looks something like this. If we glue these things together, that means the shape of the function will look a little something like this shape plus this shape plus this shape plus this shape. So when I say this shape, I mean this kind of shape goes there, this shape goes there, this shape here, and like that. We just glue our shapes together to get our kind of general shape of the function. So we know that the general shape of the graph looks something like this. We can now plot our important points that we found. Okay, what important points do we find? We found that we have a point of inflection at 1/2 1.9. So at 1/2 1.9, we have a point of inflection. We found we have a local maximum at -1, 4.16, and a local min at 2 minus 1/3. So local max at -1, 4.16, so thereabouts there, and then a local minimum at 2 minus 1/3. So we know that this is the general shape of our function. We have to hit these 3 points, and that means that the general shape of our function looks something like this. So we are increasing and concave down to the left of -1. Between -1 and 1/2, we are decreasing and concave down, so we look like this. From 1/2 to 2, we are decreasing and concave up, so we look like this. And then lastly, from 2 to infinity, we are increasing and concave up, and so we look like this. And we also know that as x gets really big, so as we go out to the right this way, our function will continue to grow. And as we go to the left, our function will continue to become increasingly large and negative. So we can plop these arrows here. And our function looks a little something like this. And if we were to plot this in something like Desmos, we would see this is a pretty accurate graph, all things considered. Let's take a look at this function. 3x to the 4th minus 8x cubed plus 6x squared plus 1. We want to graph this function. So step 1 is we're going to find our asymptotes. So we're going to take a look at the limit as x goes to infinity of our function. And again, because we have a polynomial, we only need to worry about the highest degree term. So the limit as x goes to infinity of 3x to the 4th gives us positive infinity. And the limit as x goes to negative infinity of 3x to the 4th also gives us positive infinity. Because if we take something that's negative, like increasingly large negative numbers, if we raise a negative number to the 4th power, it becomes positive. Okay, so we found our horizontal asymptotes, or our asymptotic behavior, our behavior at infinity, I should say. And now we want to find our transition points. In order to do that, as before, we're going to take a derivative. We get 12x cubed minus 24x squared plus 12x. And we're going to set that equal to 0. Okay, and if we're trying to figure out what x values make this equal to 0, it's always helpful to factor out the things that we can. Each of these coefficients is a multiple of 12, so we can factor out a 12. And in fact, each of these things has an x, so we can also factor out an x. And we get 12x times x squared minus 2x plus 1. And now we can break this apart further to be 12x times x minus 1 times x minus 1. So where are our critical points? So we have critical points at, well, x equals 0 is one critical point, because if x equals 0, then this whole thing multiplies to be 0. And also at x equals 1, because if x equals 1, both of these are 0. Okay, so we found our critical points. Now we can use those to break the number line into intervals. We get an interval from minus infinity to 0, an interval from 0 to 1, and an interval from 1 to infinity. And we're going to pick points from each of these. So I'll pick minus 10, a half, and 10. And we plug this into our first derivative. Now, what we can do is we can try and plug these into like 12x cubed minus 24x squared, but it's probably easier actually to plug it into this. Right, this, what we have here, 12x times x minus 1 times x minus 1, is the same as this, right? It's just rewritten a different way. So let's try that. And how does that help us? So f prime of minus 10 is 12 times minus 10 times minus 10 minus 1 times minus 10 minus 1. Without actually running the calculation, we can see whether this is positive or negative. Okay, because this 12 is positive, this minus 10 term is negative, this minus 10 minus 1 is negative, and then this term here is also negative. So we have a positive times a negative times a negative times a negative, which will be negative. It'll be less than 0. And of course, if you want to, you can run this calculation. Totally. You can run 12 times minus 10 times minus 11 times minus 11. You get like 121 times minus 120, whatever that is. It's a thing. But the important part is that we can just tell that this is negative. And we can do similar things for our other values. If you plug in f prime of a half, we get 12 times a half minus 1 times a half minus 1. And is this going to be positive or negative? Well, this 12 is positive, 1/2 is positive, 1/2 minus 1 is negative, 1/2 minus 1 is negative. So we have a plus, plus, minus, minus. If we multiply all those together, we're going to get something bigger than 0. And then lastly, if we plug in 10, we're going to get 12 times 10 times 10 minus 1 times 10 minus 1, which is also going to be positive because all 4 of these are positive. So what does this mean? This means that f prime is less than 0 on the interval from minus infinity to 0, and f prime is bigger than 0 on the interval from 0 to 1 and 1 to infinity. Note. Here's a thing we can note. Since the function is increasing on this interval, and it's continuous on both of them, and it's also continuous at x equals 1, we can kind of smush these intervals together. We can say instead, f is increasing on 0 to infinity. It's increasing to the left of 1, it's increasing to the right of 1, it's also continuous at 1, so that means we can just keep scooting along and we're going to keep going up. The function is increasing on this entire interval. The first derivative is increasing, so the function is increasing on that entire interval. That doesn't make too much of a difference, it's just a side note. Okay, what does this mean about our critical points? Do we have any local maximums or minimums? Well, remember, local maximums and minimums happen in places where the first derivative changes sign, and the only place that happens is at x equals 0. Because at x equals 0, the first derivative goes from being negative to being positive. So that means we have a local min at x equals 0. And just like last time, once we find our transition points, we actually want to plug them into the original function. So let's find f of 0. And in order to do that, I have a calculator here. So I've already typed in our function. We can find f of 0 equals 1. So that means we have a local minimum at x equals 1. Sorry, at the point 0, 1. Okay, we have a local minimum at 0, 1. The other types of transition points we can have are points of inflection, and those are things that involve the second derivative. So let's find the second derivative real quick. I've got the first derivative here. Let me copy that down. So if that's our first derivative, what's our second derivative? We're going to get 36x squared minus 48x plus 12. And we're going to set this equal to 0 in order to help find our points of inflection. And in order to solve this, we're going to factor out stuff that we can. So each of these coefficients, again, is a multiple of 12. So we can factor out a 12. And we get 12 times 3x minus 4 plus 1. Does this factor down at all? It does, I think. I think we get 3x minus 1 and x minus 1 equals 0. Let me just verify that that works out. If we multiply this together, we're going to get 3x squared minus 3x minus x plus 1. These combine to be minus 4x, which is exactly what we wanted, because this should be a 4x there. Okay, perfect. So this does indeed factor out. So this means we have possible points of inflection at x equals 1 and x equals 1/3. We can use these points to break the number line into intervals again. We have an interval from minus infinity to 1/3, an interval from 1/3 to 1, and an interval from 1 to infinity. And if we pick points from here, I'll pick 0, 1/2, and 10. We can do the same thing we did last time, where we can plug these into this expanded form of the second derivative, and that's going to make it a little bit easier to figure out where we are positive and negative. So f double prime of 0 is 12 times 3 times 0 minus 1 times 0 minus 1. So this is 12 times, this is negative 1, it's negative. This is negative 1, it's negative. So we have a positive, a negative, and a negative. So that means the second derivative is positive on that interval. F double prime of 1/2 is 12 times 3 times 1/2 minus 1 times 1/2 minus 1. 12 is, of course, positive. 3/2 minus 1 is positive, because you'll get positive 1/2. This is negative. You'll get negative 1/2. So we have positive minus positive. So that means this whole thing will multiply out to be negative. Then f double prime of 10 is 12. 3 times 10 minus 1. 10 minus 1. Each of these is positive. So that's going to work out to be positive. So that tells us that f double prime is bigger than 0 on the interval from minus infinity to 1/3, and the interval from 1 to infinity. And then f double prime is negative on the interval from 1/3 to 1. And so that tells us that we have points of inflection at x equals 1/3 and x equals 1. Okay, just like with our critical points, we're going to want the x, y values. So we're going to plug these into the original function. Again, let me flip back to this calculator because I already have this pulled up. F of 1 is 2, and then f of 1/3 is 1.41-ish. So let me write that down. Flip back over here. So we have points of inflection at 1/3, 1.407, and at 1, 2. So now we found all this information. How does this help us? Well, we can determine the general shape of the graph on each interval. So here's our number line. Let's plop down our critical points and our points of inflection. We found critical points at x equals 0 and x equals 1, and points of inflection at x equals 1/3, x equals 1. So we have 0, 1/3, and 1. This is not necessarily drawn to scale, but this gives us 4 intervals: an interval from -infinity to 0, an interval from 0 to 1/3, an interval from 1/3 to 1, and an interval from 1 to infinity. And now that we've done that, we're going to analyze the first and second derivative on all 4 of these intervals. Let's take a look at this interval here from -infinity to 0. What is the second derivative doing? Well, the second derivative is bigger than 0 on -infinity to 1/3. So the second derivative is bigger than 0 here and here. The second derivative is also bigger than 0 on 1 to infinity. So that means the second derivative is bigger than 0 there. But on the interval from 1/3 to 1, the second derivative is negative. And what do we know about the first derivative? Let's flip back up to the first derivative. The first derivative is negative on -infinity to 0, and it's positive everywhere else. So the first derivative is negative here, but then positive everywhere else. And so this means that on this interval from -infinity to 0, we are decreasing concave up. So that means we're going to look something like this. On the interval from 0 to 1/3, we're increasing concave up. So that means we're going to look something like this. On the interval from 1/3 to 1, we are increasing concave down. So that means we're going to look something like this. And then lastly, on 1 to infinity, we are increasing concave up. So we look something like this. If we glue all 4 of these together, we will get the general shape of our graph. Okay, so the first shape looks something like this, decreasing concave up. The second shape is increasing concave up. The third shape is increasing concave down. Oops, didn't mean to erase. Increasing concave down, and then increasing concave up again. So the general shape of the graph is a little something like this. And all we need to do is plot our important points that we found. And what important points do we find? Well, we found we have points of inflection at 1, 2, and 1/3, 1.4. So 1, 2, 1/3, 1.4. And we found we had a local minimum at 0, 1. Okay, so to the left of 0, on the interval from -infinity to 0, we look something like this. So let me draw that in. And then on the interval from 0 to 1/3, we look something like this. So let me zoom in here and draw that in. On the interval from 1/3 to 1, we're increasing in concave down, so we look like this. Let me zoom in and draw that in, like so. And then lastly, to the right of 1, we're increasing in concave up, so we look something like so. And that's plotting our function. We only need to plot 3 points. The rest of it, we just use calculus to tell us how the function is increasing, decreasing, or concave up, concave down. Let's do an example with some trigonometry, shall we? So here we have the function cosine of x plus 1/2 x. And we're on the closed interval from 0 to pi. So now instead of dealing with the entire number line, we only care about things between 0 and pi. The same general idea still applies, but instead of looking at end behavior, like what happens as x goes to positive or negative infinity, we worry about the endpoints. So we figure out our endpoints. And we do that by just plugging in. So f of 0 is cosine of 0 plus a half times 0. So that's 1 plus 0 equals 1. Then f of pi is cosine of pi plus 1/2 pi, which is minus 1 plus pi over 2, which I'm not sure what that is numerically. Let me reload this. If we have f of x equals cosine of x plus 1/2 x. Oh, that should be a plus. Sorry about that. Then f of pi gives us about 0.57. Okay, so we got our endpoints. We can plot those. That'll be helpful for us later. Let's figure out our transition points. This should sound kind of familiar because it's the exact same thing I've said the last 2 or 3 example problems. F prime of x is minus sine x plus 1/2. This is defined everywhere on our interval. So in order to find our critical points, we're going to set this equal to 0. So this tells us 1/2 is equal to sine of x. And where does this happen? If we think back to the unit circle, this will happen at x equals pi over 6 and 5 pi over 6. And so we get the following intervals. We get an interval from 0 to pi over 6, an interval from pi over 6 to 5 pi over 6, and an interval from 5 pi over 6 to pi. And we get to include 0 and pi. We're going to pick points from our intervals. I will pick 0, pi over 2, and pi. We plug into our first derivative. So f prime of 0 is minus sine 0 plus 1/2. Sine of 0 is 0, so this is just 1/2, which is positive. F prime of pi over 2 is minus sine pi over 2 plus 1/2. This is minus 1 plus 1/2, which is negative. And then lastly, f prime of pi is minus sine pi plus 1/2, which is 1/2, which is positive. So what does this mean? This means that f prime is greater than 0 on the interval from 0 to pi over 6, and the interval from 5 pi over 6 to pi, and that the first derivative is less than 0 on the interval from pi over 6 to 5 pi over 6. And what does that mean about our critical points? Are they maximums or minimums? Well, at x equals pi over 6, we have that the derivative changes from increasing to decreasing. So we have a local max at pi over 6. And by similar reasoning, we find we have a local minimum at 5 pi over 6 because the derivative changes from decreasing to increasing. Local min at 5 pi over 6. And like we said before, once we find local maximums and minimums, we want to find their actual values. So let's take a look at f of pi over 6 is 1.12. And then f of 5 pi over 6 is 0.44. And then a local min at 5 pi over 6, comma 0.44. And let me switch back to this. Okay, so I'm just writing down that information that we found. And we can find our points of inflection using the second derivative. So if our first derivative is minus sine x plus 1/2, what is our second derivative? That's right, it's just minus cosine x. What we're going to do is we're going to set this equal to 0. So what values satisfy minus cosine of x equals 0? Well, it's just the one. X equals pi over 2. Okay, so this means we get to break our interval into two subintervals, like so. We can pick points from in here. I'll pick 0 and pi because I can. Okay, and plug those into the second derivative. And that's going to give us something like this. And this tells us that f double prime is less than 0 on the interval from 0 to pi over 2, and f double prime is bigger than 0 on the interval from pi over 2 to pi. And that means that we have a point of inflection at pi over 2. But we want the xy coordinate, right? Because our end goal is to plot this on a graph. So let's figure out f of pi over 2. It's about 0.78. And now we have all the information we need. Let's draw our interval from 0 to pi. Plop down our important points, which are pi over 6, pi over 2, and 5 pi over 6. We're going to take a look at the first and second derivatives on each interval. So we have an interval from 0 to pi over 6, an interval from pi over 6 to pi over 2, an interval from pi over 2 to 5 pi over 6, and lastly an interval from 5 pi over 6 to pi. Second derivative, we found that to the left of pi over 2, the second derivative is negative, and to the right of pi over 2, the second derivative is positive. So we've got something like this. And then as far as first derivative is concerned, the first derivative is negative between pi over 6 and 5 pi over 6, and positive everywhere else. So that means it looks something like positive, negative, negative, positive. So what does that mean? Plus minus, first derivative positive, second derivative negative. What does that look like? That means we're increasing in concave down. So it looks something like this. Here we have negative, negative. That means we're decreasing in concave down like so. Minus plus means we are decreasing in concave up. And then plus plus means we are increasing in concave up. It looks something like this. So we already kind of have a general sense of how the graph will look. Let's plot our important points, and then we can plot the entire graph. So here's 0, 1, minus 1. We plot our endpoints, which we found were at 0, 1, and pi 0.57. So 0, 1, pi 0.57. Then we also draw our other important points, like so. We found we had a local maximum at pi 6, 1.12, and a local minimum at 5 pi over 6.44. So pi over 6, 1.12 right there, 5 pi over 6.44. And lastly, we had a point of inflection at pi over 2, comma 0.78. So it's a little something like that. Let me draw those more to scale. And now, what does the shape of the graph look like between these points? Well, between 0 and pi over 6, we know we look something like this. Between pi over 6 and pi over 2, we know that we look a little something like this, decreasing and concave down. Between pi over 2 and 5 pi over 6, we're decreasing and concave up. So we look a little something like this, although I didn't draw that very well. And then lastly, between 5 pi over 6 and pi, we are increasing and concave up. So that means we look a little something like that. And so with this all goes to show, with calculus, we can even draw trigonometric functions. Okay, just 2 more examples, so let's stay strong, finish this out. Here we have the function f of x equals x times e to the x. Okay, we begin by looking for our asymptotic behavior. The limit as x goes to infinity of x times e to the x. Well, as x gets really big, obviously x gets really big, e to the x also gets big. This is going to blow up to infinity. But what happens at x equals negative infinity? What's the limit as x goes to negative infinity of x e to the x? Well, this is a lot trickier, because this gets really big and negative, but this approaches 0. We have an infinity times 0. This is an indeterminate form, and this is where L'Hopital's rule can come in. In order to help us use L'Hopital's rule, we need to rewrite this as something divided by something else. And one way we can do that is to write this as the limit as x goes to minus infinity of x over e to the minus x. Now, if we try and quote-unquote plug in minus infinity, what we would get is something like minus infinity over e to the infinity. And so this is an infinity over infinity error. This is an indeterminate form. So we have an indeterminate form. And we can apply L'Hopital's rule. So what does L'Hopital's rule say? I should say, I made a video about L'Hopital's rule. It should be uploaded by this point for everyone to see. So please go watch that. It's pretty good. Not necessarily a video, but L'Hopital's rule is great. L'Hopital's rule says we can take the derivative of the top and the bottom separately, and the limit stays the same, because we are in an indeterminate form. So we get something that looks a little like this, and we can rewrite this as the limit as x goes to infinity of minus e to the x. This should be a negative infinity, sorry, which this is 0. So the limit as x goes to infinity of x e to the x is 0. Let's keep that in mind when we're going to draw our function. Now let's find our transition points. We take the first derivative using the product rule, L dr plus r dl. Derivative of x is just 1. And I'm going to rewrite this as e to the x times x plus 1. This is defined everywhere because e to the x is defined everywhere. X plus 1 is defined everywhere. So the only types of critical points we have are where the first derivative is equal to 0. This happens at x equals negative 1. Let's use that to break the number line into intervals from minus infinity to minus 1 and from minus 1 to infinity. And we can pick points from here. I'll pick 2 and 0. We plug those into the derivative. So f prime of 2 is e squared times, oh, that should be a negative 2. Sorry. Times minus 2 plus 1. E raised to powers is always positive. So this is positive, this is negative. This tells us this will be less than 0. What about f prime of 0? That's e to the 0 times 0 plus 1. This is just 1, which is positive. So we have that f prime is less than 0 on the interval from minus infinity to minus 1. And we have that f prime is bigger than 0 on the interval from -1 to infinity. So what does that mean for the point x equals -1? Well, it means it's a local minimum. We have a local minimum at x equals -1. Let's go ahead and figure out what f of -1 is. F of -1 is -1 times e to the -1, so that's -1 over e. And I don't know what that is in decimal form, so let's just go to this calculator right here. F of x equals x, e to the x. We want to find f of -1. It's about -0.37. So we have a minimum at -1, -0.37. Okay, and let me flip back to here. So that is our relative extrema. Let's find our other points of transition. That's the points of inflection. In order to do that, we need to find the second derivative. So let me rewrite the first derivative down here. So we have our first derivative here. Our second derivative, again, we use the product rule. This is our left-hand thing. This is our right-hand thing. So we get L dr plus R dl. And we can factor out an e to the x here. We get 1 plus x plus 1, which is e to the x times x plus 2. And this is defined everywhere, so we can set this equal to 0 to find our possible points of inflection. And this only happens at x equals -2, because e to the x is never equal to 0. So this allows us to break the number line into two intervals, one from -infinity to -2, and one from -2 to infinity. We can pick points. I'll pick -3 and 0 again. F double prime of -3 is e to the -3 times -3 plus 2. Let's see, e to the -3 is positive, -3 plus 2 is negative, so this will be less than 0. And then lastly, f double prime of 0 is e to the 0 times 0 plus 2, which is 2, which is bigger than 0. So this tells us that f double prime of x is less than 0 on the interval from -infinity to -2, and f double prime of x is greater than 0 on the interval from -2 to infinity. So that means we have a point of inflection at x equals -2. Let's plot this and figure out what it is. Or by plot, I mean let's calculate. F of -2 is -0.27. All right, come back here. Altogether, we have, if we draw our number line from -infinity to infinity, and we plop down our important points at -2 and -1, those were our important points, right? Yeah. We have three intervals from -infinity to -2, from -2 to -1, and from -1 to infinity. Let's take a look at the first and second derivative on each of these. We found that the second derivative is less than 0 on the interval from -infinity to -2, and bigger than 0 everywhere else. So it's bigger than 0 on -2 to infinity. And the first derivative we found is less than 0 from -infinity to -1, and bigger than 0 everywhere else. So it's less than 0, bigger than 0. What do these general shapes look like? Minus minus means we are decreasing concave down. So we're a little something like this. Minus plus means we're decreasing concave up. So we're a little something like this. And then plus plus means we are increasing concave up, a little something like this. So if we draw our axes here, what were our important points? Well, we found -2 minus 0.27 is a point of inflection. So we stretch this out a bit. 1, 2, 3. So -2 minus 0.27 is about there. We have a local minimum at -1 minus 0.37. Somewhere about there. That's not exactly drawn to scale. We also know that as x approaches negative infinity, we have a horizontal asymptote at 0. So that means that on this interval here, from -infinity to -2, the function looks a little something like this. Let me zoom in so I can try and draw better. We are decreasing concave down. Kind of something like this. On the interval from x equals -2 to x equals -1, we are decreasing in concave up. So that means, if I zoom in here, it look a little something like this. And then to the right of x equals 1, we're increasing concave up. So we're going to do a little something like this. And look at that. We only need to plot 2 points and do a little bit of calculus, and we get a pretty good looking graph for x e to the x, which is admittedly kind of a hard function to graph. It's pretty neat. All right, last example, and then we can call it a day. We want to sketch this function here. Okay, let's begin by looking at the end behavior. So the limit as x goes to positive and negative infinity. If we try and just plug in -4, or sorry, if we just try and plug in infinity, we're going to get infinity over infinity. That is a indeterminate form, so we can use L'Hopital's rule. So this says we can take the limit as x goes to infinity of 3 over 2, which is 3/2. And similarly, we can use L'Hopital's rule to find the limit as x goes to -infinity of 3x plus 2 over 2x minus 4. This would be a -infinity. So we have horizontal asymptotes of 3 over 2, both as x goes to positive and negative infinity. All right, let's find our transition points. F prime of x. In order to find this, we use the quotient rule. So that means we have the bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. And let's go ahead and simplify this because that's going to make our lives a lot easier. This is 6x minus 12 minus 6x plus 4 over, we'll keep it as 2x minus 4 squared. And we can simplify this top down more. 6x minus 12 minus 6x minus 4 over 2x minus 4 squared. We get cancellation there and there. So we get minus 16 over 2x minus 4 squared. So this is our first derivative. Okay, critical points. Let's find those. Is there anywhere where this is equal to 0? No, right? Because if a fraction is equal to 0, that means the top is equal to 0. Is there anywhere where this bottom is equal to 0? Yeah, at x equals 2. So at x equals 2, f prime of 2 does not exist. Okay, so this gives us two intervals, an interval from minus infinity to 2, and an interval from 2 to infinity. we can pick some points. I'll pick minus 10 and 10. F prime of minus 10 is minus 16 over minus 20 minus 4 squared. This is going to be negative because the top is negative, the bottom is positive because we're taking minus 24 and squaring it, we're getting something positive. So we have a negative divided by a positive. That's going to give us a negative value. And then f prime of 10 is minus 16 over 20 minus 4 squared. For the same reasoning, this is also negative. Okay, so what does this mean? This means that the function is decreasing everywhere. So f prime is less than 0 everywhere. Now notice that I didn't say that x equals 2 is a critical point, and if I did that, I misspoke. And that's because at x equals 2, the original function is undefined. So this adds another extra wrinkle. So let me change colors here. F of 2 is undefined. We have a discontinuity at 2. Discontinuity at x equals 2. What do we do with this? Okay, turns out, luckily it's for us, it's the only place where we have a discontinuity. What we do with the discontinuities if we're trying to graph it is we need to figure out the behavior of the function around the discontinuity. And you know what that means? That means we take a limit. So let's take a look at the two one-sided limits. The limit as x approaches 2 from the right of f of x. That is the limit as x goes to 2 from the right of, what's the function? 3x plus 2 over 2x minus 4. Okay, we have a lot of tools for examining limits, but we can tell that this is going to give us a positive infinity. So the limit as x goes to 2 from the right is positive infinity. If you need some help with limits, go back and watch the recorded lectures from Chapter 2. So that's one side limit, and the other limit, the limit as x goes to 2 from the left of f of x, that's the limit as x goes to 2 from the left of 3x plus 2 over 2x minus 4. This top part approaches a whole number. It approaches 8, but the bottom part approaches negative infinity. Or sorry, the bottom part approaches 0 from below, and so that means we're going to have 8 divided by negative numbers. This is going to approach negative infinity. So this is really helpful. This is going to come into play, of course, when we draw our graph. Okay. So we have x equals 2 is a point where we break up the number line because we have a discontinuity there, and we used that to find that the function is decreasing everywhere. So we got our discontinuity taken care of. We have our intervals of monotonicity taken care of. Let's take a look at if there are any points of inflection. F double prime of x. So let me copy our first derivative here. We can rewrite this to make it a little bit easier as minus 16 times 2x minus 4 to the minus 2. And that makes it a little bit easier to take the second derivative. If we want to take the second derivative of this, we can just apply the general power rule. So we get 32 times 2x minus 4 to the minus 3 times 2, which is 32 times 1 over 2x minus 4 cubed times 2, which is 64 over 2x minus 4 cubed. This is never 0. It is undefined at x equals 2. F double prime of 2 does not exist. That being said, there's not a point of inflection at x equals 2 because the original function is undefined there. But we still use this point to break the number line into two different intervals. We pick a number from both. I'll pick 0, 0 is easy to work with, and I'll pick 5, why not? And we're going to plug both of these into the second derivative. So the second derivative of 0 is 64 over 0 minus 4 cubed. That's 64 over minus 64, which is negative, less than 0. Then lastly, f double prime of 0 is, f double prime of 5, I should say, is 64 over 10 minus 4 cubed. So that's 64 over 6 cubed, which is positive because it's a positive number divided by a positive number. So the second derivative is less than 0 on the interval from minus infinity to 2. The second derivative is bigger than 0 on the interval from 2 to infinity. That means if we draw our number line here, we plop down all the important points that we found. We only have one at x equals 2. We have two intervals that we worry about, from minus infinity to 2 and from 2 to infinity. We found that the second derivative is negative over here and positive over here. And we found that the first derivative is negative everywhere. And how do we plot this? So we know that we have a vertical asymptote at x equals 2. Let me draw this line here. Because we know about how the function behaves at x equals 2, we found that, let me scroll back up here, we found that as x approaches 2 from the right, the function approaches positive infinity, and as x approaches 2 from the left, the function approaches negative infinity. Okay. We also know that to the right of 2, the function is decreasing and concave up. And what else do we know? Well, we know about our horizontal asymptotes. We know we have a horizontal asymptote at 3/2 as x goes to positive and negative infinity. So let me draw that as well. 3/2 is somewhere around here. All right. Now we have everything we need to try and draw this function. We know our horizontal asymptote, we know our vertical asymptote. To the right of 2, we are decreasing and concave up. We also know that we approach positive infinity as we approach 2 from the left, and we approach 3/2 as x goes to infinity. Lastly, we know that on the interval from minus infinity to 2, as we approach 2 from the right, the function approaches negative infinity. And we also know as x approaches negative infinity, our function approaches 3/2. We're decreasing and concave down, so that means we do something along these lines. I did not approach 3/2 very well there, but you get the idea. And that's curve sketching. I hope that made sense. The general idea is, of course, we find our transition points. That's our first and second derivative tests to find points of inflection and relative extrema. We also find discontinuities. We use those to break the number line into our intervals, and we figure out if we're concave up or down on those various intervals. And then lastly, we take a look at our asymptotic behavior. So if you have a discontinuity, we figure out the limit as x approaches that discontinuity. Like in this particular function, we found what happens as x approaches 2, how we approach positive infinity from one direction, negative infinity from the other direction. And we also figure out what happens off towards infinity. So as x gets really big, we use that information to draw a picture. Thank you so much for watching.